somewhere out in the dark, about 50 light years from where you are right now, a small star is quietly fading. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. This little star gives off a pale blue-white glow, barely visible against the black. It has no fire left inside it, no burning, no roaring fusion at its heart, and yet it still shines slowly, patiently, like an ember that refuses to go cold. That star is a white dwarf. White dwarfs are what most stars in our galaxy become when they die. Not all stars end in giant explosions. Most of them, stars like our own sun, simply run out of fuel, shed their outer layers like a coat, and leave behind a small, dense, glowing core. That core is the white dwarf. It is the final form of a star that once burned for billions of years. Right now, scientists believe that roughly 97 out of every 100 stars in the Milky Way will eventually become white dwarfs. That means almost every star you see on a clear night is either already a white dwarf, or it is slowly heading toward becoming one. The night sky is full of these quiet endings. Our own sun will become a white dwarf one day. That is not a guess. It is what the physics tells us clearly and gently. About 5 billion years from now, the sun will exhaust its hydrogen fuel, swell into a red giant star, and then collapse down into a white dwarf, roughly the size of Earth. The sun today is about 1.4 million kilometers across. The white dwarf it leaves behind will be only about 13,000 kilometers wide. That is an almost impossible shrinking. All that mass, all that gravity, all that history, pressed into something barely larger than our planet. When you look at the sun on a hazy afternoon, that pale disk of light is a star in the middle of its life. It is burning steadily, calmly, the way it has for 4.5 billion years. And somewhere far ahead in time, long after Earth has changed beyond recognition, the sun will go quiet and leave behind a small white coal drifting through space. There is something deeply peaceful about that image. The nearest known white dwarf to Earth is called Sirius B. It sits about 8.6 light years away, tucked right next to Sirius A, the brightest star in our night sky. Sirius ablaze with a brilliant blue-white light that you can see on any clear winter night in the northern hemisphere. But Sirius B, its companion, is invisible to the naked eye. It is small and dim, even though its surface burns at roughly 25,000 degrees Celsius, far hotter than our sun's surface. Its dimness comes not from being cool, but from being so incredibly small. A tiny surface, no matter how hot, does not put out much total light. Sirius B was first detected not by sight, but by math. In the mid-1800s, astronomers noticed that Sirius A wobbled slightly as it moved across the sky. Something was pulling on it, something with real mass. They predicted a hidden companion star, and in 1862, astronomer Alvin Graham Clark spotted it through a telescope for the first time. A tiny white point of light, right where the math said it would be. That moment was a quiet triumph. The universe had left a clue in the wobble of a star, and humans followed it to the answer. White dwarfs are not rare, exotic objects. They are the most common type of stellar remnant, the leftover piece of a dead star in the entire galaxy. Scientists estimate there are roughly 10 billion white dwarfs in the Milky Way alone. 10 billion of these small, cooling embers scattered through the dark between the stars, each one the ghost of a sun that once burned. Most of them we cannot see. They are simply too faint, too far away, too small to catch the light of our telescopes. They drift in silence, cooling across billions of years, carrying inside them the compressed history of everything they once were. This episode is about those stars, about what they are made of, how they hold themselves together, what happens when they find a companion, and what they will eventually become at the very end of all things. It is a quiet story, a slow one, the kind of story the universe tells best. So settle in. The stars are patient, and so are we. To understand a white dwarf, you first have to understand the star it used to be. And to understand that, you have to sit with a number that is almost too large to hold in your mind. Our sun is about 4.5 billion years old. 4.5 billion years of burning, shining, and holding our entire solar system in its grip. And here is the remarkable thing. It is only about halfway through its life. Stars like our sun live for roughly 10 billion years. 10 billion years of steady, patient burning before the end finally comes. That is a span of time so vast it has no easy comparison. If you compressed the entire history of Earth into a single day, the sun would have been burning for 2 full days before Earth even formed. It is ancient beyond anything we can truly feel. And yet, in the life of a star, it is simply normal. Stars like our sun belong to a category astronomers call main sequence stars. That phrase just means a star that is actively fusing hydrogen in its core. Fusion is the process where hydrogen atoms are pressed together so hard by gravity that they merge and form helium, releasing an enormous amount of energy as light and heat. That energy is what makes the sun shine. It is what warms your face on a summer afternoon. It has been doing this for 4.5 billion years without stopping. The sun is not especially large as stars go. Its diameter is about 1.4 million kilometers. That sounds enormous, and it is. But you can fit roughly 1.3 million Earths inside the sun. Our whole planet, the oceans and mountains, and everything living on it would fit inside the sun more than 1 million times over. And the sun is considered a medium-sized star. The universe has stars far larger and stars far smaller. What keeps a star like the sun from collapsing under its own weight is a careful balance. Gravity is always pulling inward, trying to crush the star down to nothing. But the energy released by fusion pushes outward, resisting that pull. These two forces hold each other in check for billions of years. The star neither collapses nor explodes. It simply burns, steady and bright, in a kind of long, slow equilibrium. The sun burns through an almost unimaginable amount of hydrogen every second. Each second, the sun converts about 600 million tons of hydrogen into helium. 600 million tons every single second for billions of years. And yet the sun is so large that it has enough hydrogen to keep this going for another 5 billion years before the supply runs low. The core of the sun burns at about 15 million degrees Celsius. That is not the temperature of the surface, which is already a searing 5,500 degrees Celsius. That is the temperature deep inside, where the fusion actually happens. At that depth, light takes about 100,000 years just to travel from the core to the surface. A single photon of light, born in the heart of the sun, wanders through the dense interior for 100,000 years before it finally escapes and races across space to reach us in about 8 minutes. There is something quietly wonderful about that. The sunlight touching your skin right now began its journey inside the sun long before modern humans existed. It wandered through the solar interior for tens of thousands of years, and then crossed 150 million kilometers of empty space in just 8 minutes to find you. Stars like our sun spend the vast majority of their lives in this steady state, burning hydrogen, holding the balance, shining outward into the dark. For billions of years, almost nothing changes. The star is stable, reliable, ancient. It is easy to think of stars as explosive and violent things, and they can be. But most of a star's life is quiet. Most of it is just this: the slow, patient conversion of one element into another, deep in the dark of the core, year after year, across timescales that dwarf everything we know. Our sun will do this for another 5 billion years, long after every human civilization has risen and fallen, long after the continents have rearranged themselves into shapes we would not recognize. The sun will still be burning, steady, patient, fusing hydrogen into helium 1 second at a time. But eventually, the hydrogen runs low. The balance begins to shift, and when it does, the star enters a new chapter entirely. A chapter that is stranger, grander, and more beautiful than anything that came before. That is where the story of a white dwarf truly begins. When the hydrogen in a star's core finally runs low, something remarkable begins. The core, no longer producing enough heat to push outward, starts to contract. Gravity wins a little ground. It squeezes the core inward, and that squeezing generates heat. A great deal of heat. That extra heat spreads outward into the layers of gas surrounding the core, and those outer layers respond, they expand, they swell, they push outward into space in a slow, enormous bloom that takes millions of years to complete. The star grows larger than anything we can easily picture. A star like our sun will eventually expand to hundreds of times its current size. At that point, astronomers call it a red giant, a star so large that if it sat where our sun sits now, its outer edge would reach past the orbit of Earth. The color shifts too. As the outer layers expand and cool, the star's surface temperature drops. It glows a deep, warm red instead of the bright yellow-white we see today. It is still luminous, still powerful, but it has changed its shape entirely. The way a fire looks different when it spreads wide across a hearth instead of burning in a tight flame. Inside the core, something else is happening. The helium that built up over billions of years of hydrogen fusion now becomes fuel. The core grows hot enough to fuse helium into carbon and oxygen. This is a new kind of burning, and it is less stable than what came before. The star begins to pulse. It breathes in and out over thousands of years, expanding and contracting in slow, rhythmic waves. Astronomers call this the asymptotic giant branch phase, the late stage of a star's life when it is burning helium and growing increasingly unstable. During these pulses, the star sheds its outer layers, not in a violent explosion, but in a slow, steady exhale. Shells of gas drift outward from the star's surface, pushed by the pressure of light itself. Light carries a tiny amount of force, and when a star is as bright as a red giant, that force is enough to lift gas off the surface and send it drifting into space. This process is called a stellar wind, a gentle but relentless flow of material moving outward in all directions. Over tens of thousands of years, the star loses a significant portion of its total mass this way. A star like our sun will shed roughly half of itself before the process is complete. That material does not disappear. It moves outward into the surrounding space, forming a slow-moving cloud of gas and dust that expands in a great sphere around the dying star. The star is essentially giving itself back to the universe, returning the atoms it spent billions of years fusing into something new. What remains at the center is the core. Stripped of its outer layers, the core is exposed to space for the first time. It is small. It is incredibly dense. And it is extraordinarily hot, with surface temperatures that can reach over 100,000 degrees Celsius. At those temperatures, the core blazes with ultraviolet light, the kind of high-energy radiation that is invisible to human eyes, but powerful enough to light up the surrounding cloud of expelled gas. That cloud begins to glow. The ultraviolet light from the exposed core energizes the gas, causing it to shine in colors that range from soft blue to vivid red to pale green. Seen from a distance, the whole structure looks like a glowing ring or bubble floating in space. Astronomers call this a planetary nebula, though it has nothing to do with planets. Early observers simply thought the glowing shapes looked a little like the disk of a planet through a small telescope, and the name stuck. The exposed core at the center of that glowing cloud is the White Dwarf. It did not arrive with a bang. It did not explode or collapse in a dramatic instant. It was revealed slowly, the way a stone is revealed when the tide pulls back from the shore. The outer layers drifted away. The core remained, and what remained was one of the most stable, long-lived objects in the known universe. This is how white dwarfs are born, not through violence, but through a long and patient letting go. The star releases what it no longer needs. It gives its outer layers back to space. And at the center of that gentle release, something small and dense and enduring is left behind, glowing quietly in the dark, ready to persist for longer than we can truly imagine. That glowing cloud the star left behind is not empty. It is full of gifts. A planetary nebula carries the star's outer layers outward into space. Those layers are made of real things: hydrogen, helium, carbon, nitrogen, oxygen. These are not just names on a chemistry chart. They are the raw materials of everything. Planets, oceans, living cells. All of it begins as gas drifting outward from a dying star. The hydrogen in a planetary nebula is the oldest element in the universe. It formed in the first few minutes after the Big Bang, nearly 14 billion years ago. The star gathered that ancient hydrogen when it was young. It burned it for billions of years. Now, as the star releases its outer shell, that hydrogen floats free again. It moves back into the space between the stars, ready to be gathered up by the next cloud, the next collapse, the next new sun. The helium in the nebula has a different story. The star made most of it. Deep in the star's core, hydrogen atoms were pressed so tightly together that they fused, combining to form helium. That process released light and heat. It kept the star shining for billions of years. Now that helium drifts outward in the glowing shell, carrying the record of all that ancient burning. Carbon is there too, and this is where things grow quietly remarkable. The star made its carbon through a process called the triple alpha process, where 3 helium nuclei fuse together to form a single carbon atom. The carbon in your body was made this way, not in our sun, but in stars that lived and died long before our solar system existed. Those stars released their carbon into space. That carbon drifted through the dark for millions of years. Eventually, it was swept up into the cloud that collapsed to form our sun and our planets. It settled into the earth. It became part of the rocks, the oceans, the first living things. It became part of you. The carbon atoms in your bones were forged inside a star that no longer exists. Oxygen is there in the nebula as well. Stars make oxygen in their cores during later stages of their lives, fusing carbon and helium together. The oxygen in the air you are breathing right now came from stars. Ancient stars scattered it into space. It mixed into the gas cloud that formed our solar system. It became part of Earth's early atmosphere. And later, through billions of years of change, it became the air that fills your lungs right now, in this quiet moment. Nitrogen drifts through the nebula too. It is the most common gas in Earth's atmosphere. Every breath you take is mostly nitrogen. Stars produce nitrogen through a chain of nuclear reactions called the CNO cycle, where carbon, nitrogen, and oxygen take turns helping hydrogen fuse into helium. The nitrogen in the air around you has passed through the interior of a star. Some planetary nebulae also contain traces of heavier elements: neon, magnesium, sulfur, These form in the deeper, hotter layers of more massive stars. When those stars shed their outer shells, these elements join the cloud. They spread through the galaxy slowly, mixing with older gas and dust. Over time, that enriched gas collapses again. New stars form. New planets form around them. Each generation of stars is made from slightly richer material than the last. The light from a planetary nebula comes from this gas being energized. The white dwarf at the center is extremely hot. It pours out ultraviolet radiation, which is a kind of high-energy light invisible to human eyes. That radiation strikes the surrounding gas and causes it to glow. Different elements glow in different colors. Oxygen glows green and blue. Hydrogen glows red. Nitrogen glows red-orange. The colors in a planetary nebula are a map of its chemistry. Each color tells you what element is there, how dense it is, how far it has traveled from the core. A planetary nebula does not last forever. After roughly 10,000 years, the gas spreads too thin. The glow fades. The cloud dissolves into the wider space between the stars. The elements scatter. They join the vast, slow-moving rivers of gas and dust that drift through the galaxy. But they do not disappear. They wait. They drift. They cool. And in time, gravity finds them again. The white dwarf at the center remains long after the nebula fades. It sits in the dark, no longer surrounded by its glowing cloud. The gifts have been given. The elements have been returned to space. And the small, dense core glows on alone, holding within it the quiet record of everything the star once was. That small, dense core is worth pausing on for a moment, because what remains after all that drama, after the swelling and the shedding and the glowing cloud, is something almost impossible to picture. A white dwarf is roughly the same size as Earth. Not a giant, not a vast burning sphere like the sun once was. Something closer to a small rocky world, pale and compact, sitting alone in the dark. But do not let the size fool you. The sun, before it became a white dwarf, contained an enormous amount of matter. All of that matter, the full weight of a star, is now packed into something the size of our planet. The mass did not go anywhere. The outer layers drifted away into space as the planetary nebula. But the core, the dense heart of the star, kept nearly all of its original mass. Scientists estimate that a typical white dwarf holds between 1/2 and 8/10 of the mass of our sun. All of that squeezed into a sphere roughly 12,000 kilometers across. To understand what that means, think about density. Density is how much matter is packed into a given space. A feather is not very dense. A rock is denser. A white dwarf is denser than almost anything you can imagine on Earth. A single teaspoon of white dwarf material would weigh somewhere around 15 tons. That is heavier than an elephant, heavier than a large truck, heavier than most things humans have ever built. All of that weight sitting in a space the size of a sugar cube. This extreme density comes from the way the star collapsed. When the nuclear reactions in the core stopped, there was nothing left to push outward against gravity. Gravity always pulls inward. It never stops. With no outward pressure to resist it, gravity crushed the core down with enormous force. The atoms inside were squeezed closer and closer together. The electrons, the tiny particles that orbit the center of every atom, were pressed so tightly that they could barely move. And here is where something remarkable happens. Electrons do not like to share space. This is not a preference. It is a law of physics. Electrons resist being pushed into the same state as each other. When they are compressed tightly enough, they push back. Scientists call this electron degeneracy pressure. It is not heat. It is not fire. It is a quantum force, a rule written into the nature of matter itself. And it is the only thing holding the white dwarf up. Gravity pulls inward with tremendous force. Electron pressure pushes outward with equal force. These two forces meet and hold each other still. The white dwarf does not collapse further. It does not expand. It simply holds its shape, locked in a perfect, quiet balance between two invisible giants. This balance is different from the one that kept the original star alive. A living star burns fuel. It generates heat and light and pressure through nuclear fusion. The process of smashing atoms together to release energy. That pressure balanced gravity for billions of years. But a white dwarf has no fuel left. It is not burning anything. The balance it holds is colder and stranger. It is a balance made of pure physics, not fire. Because of this extreme compression, the gravity at the surface of a white dwarf is also extreme. Surface gravity is the pull you would feel if you stood on the outer layer of an object. On Earth, surface gravity is what keeps your feet on the ground. On a white dwarf, the surface gravity is roughly 300,000 times stronger than Earth's. A person who weighed 70 kilograms on Earth would weigh around 20 million kilograms on the surface of a white dwarf. The weight would be so immense that no structure, no material, nothing we know of could survive it. The surface itself is not a soft place. There are no gentle slopes or wide plains. The extreme gravity pulls everything flat with a force that flattens even the idea of a mountain. Scientists calculate that the tallest possible feature on a white dwarf surface would be only a few centimeters high. The entire surface is essentially smooth, pressed flat by its own weight. All of this, the crushing density, the electron pressure, the immense surface gravity, comes from one simple fact. A star's worth of matter, gathered over billions of years, now lives in a space no bigger than a small planet. The universe has taken something vast and folded it small. And in that smallness, it has created something stranger and more extreme than almost anything else in the sky. And yet, for all that density and weight and crushing gravity, a white dwarf is not burning. That is the quiet miracle at the center of this section. A white dwarf produces no new energy. There is no fire inside it. No fuel is being consumed. No reactions are splitting atoms or fusing them together. The white dwarf simply glows with heat it already has, heat left over from the long, brilliant life it lived as a star. It is like a coal pulled from a fire. The coal no longer burns, but it still glows, still radiates warmth, simply because it was once so hot. To understand why this matters, think about what powered the star before it became a white dwarf. For billions of years, the star ran on nuclear fusion. Deep in its core, hydrogen atoms were pressed together by gravity so intense that they merged and became helium. That process released enormous amounts of energy. It was the same process, in a much smaller form, that powers a hydrogen bomb. The star was running that reaction continuously, every second, for billions of years. That energy pushed outward against gravity, keeping the star from collapsing. The star was always in balance, always holding itself up. When the star ran out of hydrogen, it briefly fused helium into carbon and oxygen. Then the fuel ran out entirely. The outer layers drifted away into the beautiful glowing cloud we call a planetary nebula. What remained was the core, and the core had nothing left to burn. So the white dwarf does not shine the way a star shines. It does not generate new light from new reactions. It shines the way a hot stone shines in the dark. It is releasing stored heat slowly over an almost unimaginable span of time. The surface temperature of a newly formed white dwarf can reach over 100,000 degrees Celsius. That is roughly 17 times hotter than the surface of our own sun. The sun's surface sits at about 5,500 degrees Celsius. A fresh white dwarf burns far, far hotter than that. And yet it produces that heat through no ongoing process. It simply has that heat baked into it from billions of years of stellar life. And now it is letting it go. The rate at which it lets that heat go is extraordinarily slow. Scientists estimate that a white dwarf takes billions of years to cool by even a few thousand degrees. The universe itself is only about 13.8 billion years old. That means the oldest white dwarfs we can observe have had the maximum possible time to cool, and even they are still warm. No white dwarf has had enough time to go completely cold. Not yet. Think about that for a moment. Every white dwarf ever formed is still glowing. Every single one. The universe has not yet had time to extinguish even the oldest of them. This slow release of stored heat has a name. Scientists call it thermal radiation, which simply means heat moving outward from a warm object into cooler surroundings. Everything warm does this. Your body does it right now, quietly radiating heat into the air around you. A white dwarf does the same thing, just on a scale so vast it takes trillions of years to finish. There is something deeply calming about this idea. The white dwarf is not struggling. It is not fighting to stay alive. It is simply resting, slowly sharing its warmth with the cold universe around it. It has finished its work. It has fused its hydrogen, shed its outer layers, and settled into this long, quiet release. The fire is over. What remains is the afterglow. And that afterglow is not small. Even a white dwarf that has been cooling for several billion years still shines with a pale blue-white light, visible across enormous distances. Our telescopes have found white dwarfs thousands of light years away, their faint glow still crossing the dark between stars. 1 light year is about 9.5 trillion kilometers. These stars are cooling embers, and yet we can still see them from across the galaxy. The white dwarf does not need fusion to be extraordinary. It does not need to burn. It carries its history in its heat, and that heat tells the story of everything it once was. A vast star, alive for billions of years, now folded into something the size of Earth, still warm, still glowing, still quietly present in the dark. The fire is gone. The light remains. What holds all of that together? What keeps a white dwarf from simply collapsing under its own enormous weight? There is no fusion happening inside, no fire pushing outward, no heat engine running in the core. And yet the white dwarf holds its shape, steady and still, across billions of years. The answer lies in something very small, something invisible, something that has nothing to do with heat at all. Inside a white dwarf, the atoms have been crushed so tightly that their outer shells have broken apart. The electrons, those tiny particles that normally orbit an atom's center, have been squeezed free. They no longer belong to any single atom. They move through the entire star as a dense, fast-moving sea. Scientists call this state a degenerate electron gas, which sounds complicated, but the idea is simple. The electrons are packed so closely together that they push back hard. This pushing is called electron degeneracy pressure. It is a quantum effect, meaning it comes from the strange rules that govern the very smallest things in the universe. One of those rules says that 2 electrons cannot be in the same place at the same time, doing the same thing. This is known as the Pauli exclusion principle, named after the physicist Wolfgang Pauli. Because electrons refuse to share the same space, they resist being compressed any further. They push outward with enormous force. And that force is what holds the white dwarf up. This is different from anything we experience in daily life. When you squeeze a ball, it pushes back because of heat and pressure. But electron degeneracy pressure does not care about temperature. It does not get weaker as the star cools. It does not fade with time. It is locked in by the laws of physics themselves. A white dwarf could cool to nearly absolute zero, the coldest temperature possible, and the electrons would still be pushing outward with the same force. The star would still hold its shape. This is why white dwarfs can survive for so long. They are not burning. They are not fighting. They are simply obeying physics. Now imagine floating above the surface of a white dwarf. The first thing you would notice is the light. It is not the warm golden glow of our sun. It is pale and blue-white, like the color of a very hot flame or the coldest part of a candle. The surface temperature of a newly formed white dwarf can reach 100,000 degrees Celsius. Even older, cooler white dwarfs still glow at tens of thousands of degrees. The light they give off is fierce and clean and very, very blue. The surface itself would look almost perfectly smooth. There are no mountains here. No valleys, no craters carved by ancient impacts. The gravity on a white dwarf is so intense, roughly 300,000 times stronger than Earth's gravity, that nothing could stand tall against it. Any raised feature would be pulled flat almost instantly. Scientists estimate that the surface of a white dwarf is smoother than the finest polished glass. The entire star is a sphere so close to perfect that the human eye could not detect any flaw in its curve. The atmosphere above that surface is almost nothing. Just a thin, ghostly layer of gas, mostly hydrogen or helium, clinging to the star by gravity alone. It is so thin that, if you could somehow stand in it, it would feel like standing in a near-perfect vacuum. And yet, even this whisper of atmosphere has structure. It bends and filters captures the light rising from below, giving the star its color, shaping what distant telescopes can read about its chemistry. There is no wind here, no weather, no storms rolling across the surface. The white dwarf is quiet in a way that is almost hard to imagine. On Earth, the air is always moving. Oceans churn, clouds form and dissolve, but a white dwarf has none of that. Its surface is still. The only thing happening is the slow, patient release of heat, rising up through that thin atmosphere and drifting outward into the dark. And yet, this stillness is not emptiness. The electrons deep inside are still moving. They are still pushing. They are still holding everything in place with a force that does not weaken, does not tire, does not ask for anything in return. The surface may look calm, but underneath, the smallest particles in the universe are doing something remarkable. They are refusing to give way. They are holding an entire dead star together, quietly, faithfully, across all the long years of cooling. The surface is still. The foundation is not. That foundation has a limit, though. Everything does. And for a white dwarf, that limit has a name and a number, and both of them matter enormously. In the 1930s, a young Indian physicist named Subramanian Chandrasekhar was traveling by ship from India to England. He was just 19 years old. During that long ocean voyage, he did the math. He worked out exactly how much mass a white dwarf could hold before its own gravity became too strong for the electrons inside to resist. The number he arrived at was about 1.4 times the mass of our sun. Scientists now call this the Chandrasekhar limit, and it remains one of the most important numbers in all of astronomy. Think about what that means. The electrons inside a white dwarf push back against gravity with a force called electron degeneracy pressure. That pressure is extraordinary. It holds a dead star together across billions of years without needing any fuel at all. But it is not infinite. There is a ceiling. If a white dwarf ever gains enough mass to push past that ceiling, the electrons can no longer hold. The pressure fails, and when it fails completely. Below that limit, the white dwarf is stable. It simply sits there, cooling slowly, holding its shape, doing nothing dramatic. It could do this for longer than the current age of the universe and never change in any meaningful way. The electrons keep pushing. Gravity keeps pulling. They balance each other perfectly, and the star just rests in that balance, patient and still. But the interior of a white dwarf is not perfectly uniform. Beneath the thin atmosphere and the hot outer layers, the structure changes as you go deeper. The outer regions are made mostly of carbon and oxygen. The ash left over from the nuclear burning that happened during the star's earlier life. These atoms are packed together with extraordinary tightness. There is no space between them the way there is in ordinary matter. The electrons have been stripped away from their parent atoms entirely. They move freely through the interior, not bound to any single nucleus, forming a kind of dense, flowing sea of charged particles. Deeper still, the pressure grows even more intense. The carbon and oxygen nuclei, the cores of those atoms, are squeezed closer and closer together. Scientists believe the very center of a white dwarf may behave more like a liquid than a solid, despite the crushing density. The particles there are so tightly packed and moving in such specific ways that the usual rules about solid and liquid start to blur. It is matter in a state that has no easy comparison to anything we encounter in daily life. And all of this is invisible. No telescope can see inside a white dwarf directly. The interior is hidden beneath layers of hot, glowing gas. What scientists know about the inside comes from careful observation of how white dwarfs vibrate, how they cool, how their gravity behaves. It is a little like learning what is inside a drum. By listening to the sound it makes when you tap it. The outside tells you something about the inside if you know how to listen. What makes the Chandrasekhar limit so remarkable is that it is not just a number about white dwarfs. It is a number that connects to the fate of the entire star. A white dwarf that stays below 1.4 solar masses will cool quietly for an almost unimaginable stretch of time. A white dwarf that somehow gains mass and crosses that line will not survive. It will collapse or explode or transform into something else entirely. The limit is a kind of threshold between two completely different futures. Chandrasekhar published his findings and was largely dismissed at first. The great British astronomer Arthur Eddington publicly rejected his work, calling it absurd. It took decades for the scientific community to accept that the young man on the ship had been right all along. In 1983, Subramanian Chandrasekhar received the Nobel Prize in Physics. The limit that bears his name is now taught in every astrophysics course in the world. There is something quietly moving about that story. A teenager on a boat, doing math by hand, working out the fate of dying stars. The universe does not care about our timelines or our doubts. The physics was always true. The limit was always there, waiting to be found. And deep inside every white dwarf, the electrons keep pushing against it, holding the line, holding the star, holding everything together for as long as they possibly can. And so a white dwarf simply waits. It holds its shape. It holds its electrons in place. And slowly, over time, it begins to change color. This is one of the quietest cycles in the universe. No explosion, no drama, just a star cooling down degree by degree across billions of years. And as it cools, its color shifts, like a piece of iron pulled from a forge, glowing white, then yellow, then orange, then red. The white dwarf moves through the spectrum of light in a long, slow procession. When a white dwarf is young, it burns with fierce blue-white light. The surface temperature at this stage can reach 100,000 degrees Celsius or more. At those temperatures, the star pumps out enormous amounts of ultraviolet light, the kind of high-energy radiation that human eyes cannot see. But the visible light it does release is intensely blue-white, sharp and bright against the darkness of space. This is the color of youth in stellar terms. The white dwarf has just shed its outer layers. The planetary nebula around it is still glowing. The core is exposed and raw and searingly hot. If you could somehow stand at a safe distance and look at it, it would look like a tiny, fierce blue-white point of light, far smaller than our sun, but far hotter at its surface. Over millions of years, that surface begins to cool. The color shifts. Blue-white becomes white. White becomes yellow-white. The star is still extraordinarily hot by any human measure, but it is losing its heat slowly, radiating it out into the surrounding space with no internal engine to replace what it loses. There is no fusion happening inside. There is no new energy being made. The white dwarf is living off what it already has, and that supply is finite. Scientists classify stars by their surface temperature using a system called spectral type. White dwarfs move through these classifications as they age. A very hot young white dwarf sits at the top of the scale. As it cools across hundreds of millions of years, it slides down toward cooler and cooler classifications. Astronomers can look at the color of a white dwarf and estimate how long it has been cooling. Color becomes a kind of clock. This is one of the ways scientists use white dwarfs to measure the age of star clusters, groups of stars that all formed around the same time. The coolest, dimmest white dwarfs in a cluster are the oldest ones. They have been cooling the longest. By studying how dim and red they have become, scientists can work backward and estimate when that cluster was born. The color of a dying star tells us when it lived. Our own sun will one day follow this same path. After it swells into a red giant and sheds its outer layers, its core will be left behind as a white dwarf. At first, it will glow blue-white and fierce. Then it will cool to white, then yellow, then orange. Over trillions of years, it will fade toward red. And then, if enough time passes, it will become something so dim and cool that it barely glows at all. Scientists call this theoretical end state a black dwarf, a cold, dark remnant of what was once a living star. But we will return to that idea later. For now, picture the cooling as a kind of breathing out. The star has spent billions of years burning, fusing, radiating, pushing outward with tremendous force. And now it exhales, slowly, across timescales that make human history feel like a single heartbeat. The color change is that exhale made visible. There is something deeply calming about this cycle. It mirrors things we already know. The way a fire dies down from roaring orange to quiet red to fading ember. The way the sky shifts from noon blue to golden dusk to the deep violet of evening. The universe uses the same language everywhere: heat and light and color, moving together in one direction, cooling and dimming and settling toward stillness. Every white dwarf in the sky tonight is somewhere along this path. Some are young and blue-white and blazing. Some are older and yellow and quiet. Some are ancient and orange-red, barely visible, nearly spent. Each one is a record of time. Each one is a clock made of light, ticking not in seconds, but in billions of years. And all of them are cooling. All of them are moving slowly and without hurry through the long spectrum of their final chapter. The universe is patient. It has time for all of it. The surface of a white dwarf is one of the strangest places in the universe. It is impossibly hot. It is almost perfectly still, and it sits exposed to the void of space with nothing above it. No atmosphere worth speaking of, no weather, no wind. Just the raw, glowing surface of a dead star, radiating its ancient heat into the dark. When a white dwarf is young, its surface temperature can reach 100,000 degrees Celsius or more. That is nearly 20 times hotter than the surface of our own sun. Hold that number gently for a moment. Our sun, that enormous burning star that warms every living thing on Earth, is cool by comparison to a freshly born white dwarf. The heat pouring off that tiny, dense surface is almost beyond imagining. And yet, the white dwarf makes no new heat of its own. Everything it radiates was stored long ago, locked inside when the star was still alive and fusing hydrogen in its core. Now it simply releases that stored energy slowly and steadily, the way a stone pulled from a fire stays warm long after the flames are gone. The surface glows not because anything is burning, but because the heat has nowhere else to go. What makes the surface so unusual is how small it is. A typical white dwarf is roughly the size of Earth, maybe a little larger, but it carries the mass of an entire star compressed into that small sphere. The gravity at the surface is staggering. It is roughly 300,000 times stronger than the gravity you feel standing on Earth right now. If you could somehow place a single grape on the surface of a white dwarf, the gravity would crush it instantly into something far smaller than a grain of sand. The the surface itself is not a place anything could survive. It is a place of crushing, silent, extreme force. Because the gravity is so intense, the surface of a white dwarf is remarkably smooth. Astronomers believe any mountains or variations in the surface would be pulled flat almost immediately. The gravity simply does not allow for roughness. The surface settles into something very close to a perfect sphere, polished by its own weight into a shape that is almost mathematically precise. There is something quietly beautiful about that. The most violent forces in the universe producing something so clean and still. The surface also interacts with space in a way that feels almost lonely. A white dwarf has no solar wind, no stream of charged particles flowing outward the way our sun constantly breathes particles into the solar system. The sun's solar wind shapes the space around it for billions of kilometers, pushing against the edges of the heliosphere, that vast bubble of influence our star creates. A white dwarf has lost that breath. It no longer pushes outward. It simply sits, glowing, surrounded by the quiet of space. If a white dwarf has any planets orbiting it, those planets exist in a very different kind of neighborhood than Earth does. The white dwarf still gives off light and heat, but far less than a living star. Any planet that once orbited the original star at a comfortable distance would now find itself in a much colder, dimmer environment. Scientists have found evidence that some white dwarfs do have surviving planetary bodies nearby, rocky remnants that outlasted the death of their star. They orbit in silence around a cooling ember, bathed in faint light, drifting through the long dark. The space immediately around a white dwarf is also remarkably calm. No flares erupt from its surface the way they do from active stars. No massive eruptions of plasma shoot outward into space. The white dwarf simply radiates. It is the quietest kind of stellar object, doing nothing dramatic, just slowly releasing what it has stored degree by degree across timescales that stretch into the billions of years. That quiet is part of what makes white dwarfs so compelling. The universe is full of violent, dramatic events. Stars explode. Black holes tear matter apart. Galaxies galaxies collide in slow motion over millions of years. But the white dwarf sits apart from all of that. It has already done its work. It fused its hydrogen. It shed its outer layers. It compressed itself into something dense and small and enduring. And now it simply cools, patiently, without drama, surrounded by the vast silence of space, radiating its ancient warmth into the dark, 1 degree at a time. The surface is extreme in every measurable way, and yet somehow it feels peaceful. A place of tremendous heat and tremendous stillness, existing together quietly in the long night of the universe. What a white dwarf is made of tells us something remarkable about stars themselves. These dense, quiet objects are not made of ordinary rock or metal the way planets are. They are made of the very atoms that stars spent billions of years building, fused together in the heart of a dying sun, and left behind when all the burning was done. Most white dwarfs are made almost entirely of carbon and oxygen. These two elements are the ash left over from a star's final stage of fusion. When a sun-like star runs out of hydrogen, it begins fusing helium instead. That helium fusion produces carbon and oxygen. When the helium runs out too, the star can no longer sustain the process. It sheds its outer layers and leaves behind a core packed with those two elements, compressed into a sphere roughly the size of Earth. Carbon and oxygen are not exotic or rare. Carbon is the same element found in every living thing on Earth. Oxygen is the same element you breathe right now. But inside a white dwarf, these familiar atoms exist under conditions nothing on Earth could ever match. They are squeezed so tightly together that the normal rules of matter no longer apply. The atoms are not arranged in any crystal structure yet. They move freely like a liquid, but without the heat-driven chaos of a true liquid. Scientists call this state a degenerate gas, meaning the electrons inside are packed so tightly they can barely move at all. Some white dwarfs are made of something slightly different. Stars that were more massive than the sun, but not quite massive enough to explode as supernovae, can leave behind white dwarfs made primarily of oxygen, neon, and magnesium. These heavier elements form when a more powerful star pushes its fusion further before it dies. These white dwarfs are rarer, and they tend to be slightly more massive than the carbon-oxygen variety. The most extreme white dwarfs in terms of composition are the ones that sit right at the upper edge of what is possible. A white dwarf can only hold so much mass before gravity overwhelms the pressure holding it up. The most massive white dwarfs ever observed sit very close to that upper limit. They are made of the heaviest elements their parent stars could produce, compressed into objects so dense that a single cubic centimeter of their interior material would weigh hundreds of thousands of kilograms. The lightest white dwarfs are interesting in a different way. Some white dwarfs appear to be made almost entirely of helium. These are called extremely low-mass white dwarfs, and they are puzzling because a single star should not be able to produce one on its own. A star would need far longer than the current age of the universe to shed enough mass naturally to leave behind a helium core white dwarf. Scientists believe these objects form in binary systems, where a companion star strips away the outer layers of its partner before the full fusion process can complete. The result is a white dwarf that never finished its work, a stellar remnant made of the lightest possible material. The interior of a white dwarf is also layered like an onion. The carbon and oxygen core sits at the center. Around that core, there is often a thin shell of helium. Around the helium sits an even thinner layer of hydrogen, the lightest element of all. These outer layers are incredibly thin compared to the size of the whole star. The hydrogen layer on a typical white dwarf might account for only 1/10,000th of the star's total mass. Yet that thin veil plays an enormous role in what we can observe from Earth, shaping the light the white dwarf sends out across space. What makes all of this so striking is the sheer variety hidden inside objects that look, from a distance, like simple points of light. Every white dwarf carries a record of the star it came from. The composition of its core reflects the mass of its parent, the length of its life, and the conditions inside its heart during those final stages of burning. Reading a white dwarf's composition is like reading a letter written billions of years ago by a star that no longer exists. The universe keeps these records carefully. Nothing is wasted. The carbon and oxygen locked inside a white dwarf today may one day be scattered across space, seeding new clouds of gas and dust, contributing to new stars, new planets, new possibilities. Even in its quiet, cooling state, a white dwarf holds within it the raw material of everything that might come next. The story of what it is made of is also the story of what the universe will make next. That thin veil sitting above a white dwarf's core is one of the quietest, most delicate things in the known universe. It is barely there, and yet it shapes everything we see. Most white dwarfs wear a thin outer layer of hydrogen gas. Beneath that sits a slightly thicker layer of helium. These two layers sit on top of the carbon and oxygen core, like the thinnest possible coating of frost on a stone. The hydrogen layer is only about 1/10,000th of the star's total mass. The helium layer beneath it is a little thicker, but still remarkably small. Together, they make up almost nothing, and yet they define almost everything about how the star appears to us. Here is why that matters. When light travels up from the hot interior of a white dwarf, it passes through these outer layers before it reaches space. The atoms in those layers absorb certain colors of light and let others pass through. Scientists study which colors arrive and which ones are missing. That pattern of missing colors tells them exactly what the atmosphere is made of. It is a kind of fingerprint. Each element absorbs its own specific colors, and no two elements absorb the same ones. So by reading the light, scientists can read the star. White dwarfs with hydrogen-rich atmospheres are called Da white dwarfs. This is the most common type. Roughly 8 out of every 10 white dwarfs belong to this group. Their spectra, the patterns of light they produce, show the clear signature of hydrogen and almost nothing else. The hydrogen sits on top, and it hides whatever lies beneath. White dwarfs without that hydrogen layer, ones whose outer atmosphere is made mostly of helium, are called Db white dwarfs. They are less common. Their light looks different. The helium signature is distinct, cooler in feel, quieter in its pattern. Scientists have spent decades trying to understand why some white dwarfs lose their hydrogen layer and others keep it. The answer involves the slow, gentle settling of elements inside the star over millions of years. Gravity on a white dwarf is extraordinary. It is roughly 100,000 times stronger than the gravity you feel standing on Earth. That intense pull drags heavier elements downward very quickly. Hydrogen, being the lightest element, floats. It stays on top. Helium, slightly heavier, settles just beneath it. Heavier elements like carbon and oxygen sink deeper still. This process is called gravitational settling, and it works constantly, silently, sorting the star's material by weight the way a river sorts sand and stone. Because of this settling, the atmosphere of a white dwarf becomes purer over time. A young white dwarf might have a mixed outer layer, but as millions of years pass, the heavier elements sink away, and only the lightest remain on top. The star slowly simplifies itself. Its surface becomes cleaner, quieter, more uniform. It is a kind of slow tidying, driven by nothing more than the patient pull of gravity. There is something almost meditative about this. A white dwarf just sits there, cooling, while gravity does its quiet work below the surface. No explosions, no dramatic events, just the steady, unhurried sorting of atoms, one by one, sinking toward the center over timescales that dwarf human imagination. Some white dwarfs show signs of both hydrogen and helium mixed together in their outer layers. These are called DAB or DBA white dwarfs, depending on which element dominates. Scientists believe this mixing happens when the star passes through a certain temperature range during cooling. At those temperatures, the boundary between the hydrogen and helium layers becomes unstable. The two layers stir together briefly, like oil and water being gently shaken, before settling again into their separate zones. It is a temporary mixing, a small moment of disorder in an otherwise very orderly process. There are also white dwarfs with traces of carbon in their outer atmosphere. These are called DQ white dwarfs. The carbon dredges up from deeper layers as the star cools, and its outer zone slowly churns. Seeing carbon in the atmosphere tells scientists something about the depth of the helium layer and the temperature at which the mixing occurs. Every variation, every subtle difference in the spectrum carries information. The star is always communicating, always sending out its quiet record of what is happening inside. The atmosphere of a white dwarf is thin enough to seem almost invisible. But it is one of the richest sources of information astronomers have. It holds the history of the star's cooling, the strength of its gravity, the depth of its layers, and the slow movement of matter over billions of years. In the smallest details, the universe hides its most careful records. Sometimes the universe hides its secrets in plain sight. For decades, astronomers noticed something strange in the spectra of certain white dwarfs. A spectrum is the spread of light from a star, broken into its colors the way a prism splits sunlight into a rainbow. Each element leaves its own mark in that spread of color, like a fingerprint. And in some white dwarfs, the fingerprints did not make sense. These stars showed traces of heavy elements in their atmospheres: calcium, iron, magnesium, silicon. This was deeply puzzling. A white dwarf's gravity is so strong that it should pull heavy elements down and out of sight very quickly. Within days or weeks, anything heavier than hydrogen or helium should sink below the surface, swallowed by the star's crushing pull. The atmosphere should be clean, pure, simple, but it was not. Early astronomers who spotted these traces were not sure what to make of them. Some thought the heavy elements might be rising up from inside the star. Others thought there might be errors in the measurements. The instruments of the early 20th century were good, but not perfect. It was easy to doubt a strange result when the expected answer seemed so clear. The atmosphere of a white dwarf should be clean. That was the theory. And for a long time, the strange signals were set aside. The real shift came slowly as telescopes improved and spectrographs became more sensitive. A spectrograph is an instrument that captures and records the fingerprints of light with great precision. By the late 20th century, astronomers could measure the chemical makeup of a white dwarf's atmosphere with remarkable accuracy. And the more carefully they looked, the more heavy elements they found, not in one or two stars. In a large fraction of all white dwarfs observed, scientists now estimate that somewhere between 25 and 50% of all white dwarfs show these traces of heavy elements. The pattern was too common to be a mistake. The answer, when it finally came together, was both logical and quietly astonishing. The heavy elements were not rising from inside the star. They were falling in from outside. Something was delivering rocky material to the surface of the white dwarf. Something was being torn apart and consumed. That something was the remnants of a planetary system. When a star swells into a red giant and then sheds its outer layers, the planets and asteroids orbiting it do not simply vanish. Some are destroyed in the expansion, but others survive, their orbits now disturbed by the sudden loss of the star's mass. Gravity shifts, orbits change. Rocky bodies that once moved in stable paths begin to drift. Some of them wander too close to the white dwarf. The star's tidal force, the difference in gravity between the near side and the far side of an object, stretches and tears the rocky body apart. It breaks into a stream of dust and debris that forms a disk around the white dwarf. Over time, that material spirals inward and falls onto the surface. The heavy elements sink quickly, but new material keeps arriving, keeping the signal alive in the atmosphere. This discovery changed the way scientists think about white dwarfs entirely. The polluted atmosphere is not a flaw or a mystery. It is a record. It is a chemical sample of a destroyed world, delivered directly to the surface of the star for astronomers to read. The scientist who helped bring this picture into focus was a researcher named David Coaster, along with many collaborators who studied the sinking timescales of different elements. By calculating how fast each element should sink in a white dwarf's gravity, they could work backward. They could figure out how much of each element was being delivered and in what proportions. And those proportions matched the composition of rocky planets and asteroids. The white dwarf was eating the remains of its own solar system, and the meal was leaving a record in the light. Some white dwarfs show traces of water-bearing minerals in their consumed material. This tells scientists that the destroyed bodies once held water, perhaps in abundance. The same building blocks that made Earth wet and alive were present in those distant, shattered worlds. The white dwarf carries their memory now, written in calcium and iron, and the faint shimmer of elements that once made up mountains and oceans on worlds that no longer exist. It is a quiet kind of discovery. No explosion, no dramatic moment, just a careful scientist looking at a spectrum, noticing something that should not be there, and asking why. The answer took decades to arrive, but it revealed that white dwarfs are not just the remnants of stars. They are the graveyards and the archives of entire solar systems, holding the chemistry of lost worlds in their thin and ancient air. Most stars in our galaxy do not travel alone. More than half of all the stars you see on a clear night exist in pairs, or sometimes in groups of 3 or more. They orbit each other, bound by gravity, circling a shared center point, the way 2 dancers might circle each other across a quiet floor. When one of those paired stars dies and becomes a white dwarf, the story does not end. It changes. A white dwarf in a binary system, that is, a system where 2 stars orbit each other, lives a very different life than one that drifts alone through the dark. The companion star is still there, still burning, still close, and the white dwarf, dense and powerful as it is, begins to feel that presence in ways that can reshape everything. The first surprise is just how common this situation is. Scientists estimate that a large portion of all white dwarfs have a companion of some kind. That means the quiet, cooling objects we have been describing throughout this episode are often not quiet at all. Many of them are locked in a slow, gravitational conversation with another star. And that conversation can last for billions of years. The 2 stars in a binary system do not need to be the same size or the same age. In many cases, one star burns through its fuel faster than the other. The more massive star evolves more quickly, swells into a red giant, sheds its outer layers, and becomes a white dwarf, all while its smaller companion is still living a relatively normal life. So you end up with a pairing that looks almost mismatched. tiny, dense white dwarf on one side, a younger, larger, still burning star on the other. They continue to orbit each other, sometimes separated by a distance smaller than the distance between Earth and our Sun. That closeness matters enormously. When two stars are that near to each other, gravity does not simply hold them in orbit. It begins to reach. The white dwarf's gravity is extraordinary. It is the compressed mass of an entire star packed into a sphere the size of Earth. That gravity pulls outward toward its companion with quiet, relentless force. Some binary systems are so close that the two stars are nearly touching. In these cases, the outer layers of the companion star can actually begin to stretch toward the white dwarf, pulled by that powerful gravitational grip. The companion does not explode. It does not break apart all at once. Instead, material flows from it slowly, like water tilting across a surface toward a drain. This process has a name. Scientists call it mass transfer, and it is one of the most important and dramatic processes that white dwarfs can undergo. What happens next depends on how fast that material arrives and how much the white dwarf can absorb. In some systems, the transfer is slow and steady. In others, it builds and builds until something gives way. The white dwarf grows heavier over time. It accumulates new material on its surface, and that accumulation changes everything about what the white dwarf is and what it might become. Here is something that surprises even people who study stars for a living. A white dwarf that gains enough mass from its companion can actually approach a kind of critical threshold. It begins to grow toward the limit that defines how much a white dwarf can weigh before its internal pressure can no longer hold it together. The white dwarf is, in a sense, being fed toward its own potential destruction. The companion star that shares its orbit may ultimately be the thing that ends it. But there is something almost tender in this arrangement, too. These two objects have been bound to each other since before either of them died or changed. They formed from the same cloud of gas and dust billions of years ago. They have orbited each other through the long, slow ages of stellar life. And now, in this late chapter, one of them continues to give, Material flows from the living star to the dead one. Energy passes between them. The system continues to evolve, to change, to produce new phenomena that neither star could produce alone. The universe rarely lets things simply stop. Even a white dwarf, which we might imagine as a final resting place, can be stirred back into activity by the right companion. It is one of the quieter surprises of stellar science. Not every ending is solitary. Not every remnant drifts alone. Some of the oldest, coolest, most exhausted objects in the galaxy are still, even now, caught up in something larger than themselves, still being shaped by a relationship that began before our sun existed. That flow of material between two stars is one of the most elegant processes in all of stellar science. It happens slowly, over millions of years, in near-perfect silence, and it begins with gravity. A white dwarf is extraordinarily dense. Even though it is roughly the size of Earth, it carries the mass of an entire star. That mass produces a gravitational pull of tremendous strength. When a white dwarf shares its orbit with a companion star, that pull does not simply hold the two objects together. It reaches out. It tugs at the outer layers of the living star beside it. The companion star in many of these systems is what astronomers call a red giant. A red giant is a star in a late stage of its life, one that has swelled to many times its original size. Its outer layers are loosely held, stretched thin across an enormous volume. The white dwarf's gravity finds those outer layers and begins to pull. This process has a name. Scientists call it mass transfer, and it is exactly what it sounds like. Mass moves from one star to the other. Hydrogen and helium from the surface of the living star drift across the space between them, drawn steadily toward the white dwarf's powerful gravity. It is not a violent tearing. It is more like a slow, continuous pour. The material does not fall straight down onto the white dwarf surface. As it crosses the gap between the two stars, it carries angular momentum, which is the spinning energy of its original orbit. That spinning motion causes the gas to spread out into a flat, rotating ring around the white dwarf. Astronomers call this structure an accretion disk. Accretion simply means the gathering of material over time. An accretion disk glows. As the gas spirals inward, it compresses and heats up. The inner edges of the disk can reach temperatures of tens of thousands of degrees. From a distance, this glowing ring would look like a soft halo of light surrounding the white dwarf, shimmering in shades of white and pale blue. It is one of the more visually striking structures in the universe. The gas continues to spiral inward until it finally settles onto the white dwarf's surface. Layer by layer, the white dwarf gains new material. This is not a neutral event. The white dwarf's surface is already extraordinarily hot, and the arriving hydrogen is compressed under intense gravity. The conditions are extreme in a way that is difficult to fully picture. Here is where the connection between these two stars becomes something more than a simple exchange. The white dwarf is not just collecting material. It is transforming it. The hydrogen that arrives from the companion star is pressed down under the weight of the white dwarf's gravity until it reaches temperatures and pressures that trigger nuclear fusion. Fusion is the process where atoms are forced together to release enormous energy. This is the same process that powers ordinary stars. But here it happens in a thin shell on the surface of a dead one. This is the white dwarf briefly doing something it has not done in a very long time. It is burning again in a small and temporary way. The energy that builds up in that thin hydrogen shell will eventually release all at once, producing a sudden flash of light. That event has its own name, and it belongs to the next part of this story. But the slow theft that leads to it is worth pausing on. What is remarkable here is the scale of the connection. Two stars, separated by millions of kilometers, are exchanging matter and energy across that distance in a continuous, organized flow. The gravity of one reaches into the body of the other. The material that was once part of a living star becomes fuel for a dead one. The dead one processes that fuel and sends light back out into the galaxy. Nothing in this system is isolated. The white dwarf shapes the companion star by pulling material away from it. The companion star shapes the white dwarf by feeding it. The accretion disk connects them visually, physically, energetically. Each object changes because of the other. Each object's future depends on what the other provides. This is how the universe tends to work, not in isolation, but in relationship. Stars are born in groups from the same clouds of gas. They age together. They die at different rates. And even after one of them has collapsed into a quiet, cooling remnant, the bond between them continues to produce new events, new light, new change. The white dwarf pulls from its partner. The partner gives. And the system, ancient as it is, keeps moving forward. And then sometimes the system does something remarkable. The white dwarf has been pulling hydrogen from its companion star for a very long time. Slowly, patiently, that hydrogen settles onto the white dwarf surface. It does not fall and disappear. It builds up, layer by thin layer, like snow gathering on a rooftop over a long winter. The white dwarf holds this borrowed hydrogen in a thin shell pressed tight against its surface. And it waits. The waiting can last thousands of years. The hydrogen keeps arriving. The layer keeps growing thicker. The pressure at the bottom of that layer keeps climbing. The temperature there rises too, slowly and steadily, in a way that cannot be seen from the outside. Nothing about the system looks unusual. The two stars continue their slow orbit. The accretion disk continues its quiet spin. But deep inside that thin hydrogen shell, something is building. Then the pressure crosses a threshold. The temperature at the base of the hydrogen shell reaches roughly 10 million degrees. At that point, nuclear fusion ignites. Not inside the white dwarf's core, where fusion ended long ago, but right there on the surface, in that thin, stolen shell. The reaction does not start slowly. It runs away almost instantly, spreading across the entire surface of the white dwarf in a matter of seconds or minutes. The energy released is enormous. This event is called a nova. The word comes from the Latin term for new star, because that is exactly what ancient astronomers thought they were seeing. A star that had not been visible before would suddenly appear in the sky, bright enough to see without a telescope. Then, over days or weeks, it would slowly fade. The star was not new, of course. It was an old white dwarf, briefly wrapped in in a shell of nuclear fire. During a nova, the white dwarf can become 10,000 to 100,000 times brighter than it normally appears. That surge of light travels outward across the galaxy. If the system is close enough to Earth, the nova can be seen with the naked eye, glowing like a new point of light in a familiar constellation. Some novas have been bright enough to cast faint shadows at night. The explosion does not destroy the white dwarf. That is one of the most important things to understand about a nova. The white dwarf survives. The fusion burns through the hydrogen shell and blasts the outer material away into space. A shell of glowing gas expands outward from the system, lit up in reds and oranges and pale blues. It drifts away slowly, thinning as it goes, until it becomes invisible. The white dwarf sits at the center, largely unchanged. A little hotter, perhaps. A little lighter, having shed the hydrogen it accumulated, but still there. And then the process begins again. The companion star is still there. Its gravity still holds it in orbit. The white dwarf's gravity is still reaching across the space between them. The accretion disk reforms. Hydrogen begins to flow again. The thin shell begins to build again. Thousands of years from now, the pressure will climb again. The temperature will cross that threshold again. And another nova will light up the sky. Some binary systems are known to produce novas repeatedly, over and over, across enormous spans of time. These are called recurrent novas. Scientists have observed the same system flare more than once in recorded history, confirming that the cycle truly repeats. There is something quietly astonishing about this. A star that should be finished, that has used up its fuel and collapsed into a cooling remnant, keeps producing light. Not from its own reserves, but from what it receives. The white dwarf transforms borrowed hydrogen into brief, brilliant fire. It does not last, but it is real. It is measurable. It is visible from other star systems entirely. The universe does not let things simply stop. Change moves slowly in most places, across timescales that are hard to imagine. But the change is always happening. The white dwarf is not the same object it was 1,000,000 years ago. It has pulled material from its companion, built up layers, ignited them, shed them, and started over. Each cycle leaves a faint trace. Each nova shell drifts a little farther out into the surrounding space, carrying the chemical fingerprints of both stars. The system keeps changing. The white dwarf keeps changing. And in those brief moments when the hydrogen shell ignites and the light blazes outward, the universe takes notice. A point of fire appears where there was only darkness. It holds for a little while. Then it fades, and the quiet, patient work begins again. But sometimes the quiet, patient work does not begin again. Sometimes the white dwarf pulls in too much. The mass it has stolen from its companion star crosses a threshold it cannot survive. And what happens next is one of the most violent and beautiful events the universe produces. The white dwarf does not simply flare. It does not simply brighten for a few weeks and fade. It tears itself apart in a single catastrophic explosion. It becomes a type Ia supernova, and the light it releases in that moment is almost impossible to describe. A type Ia supernova shines with the brightness of several billion suns. Not millions, billions. A single exploding white dwarf, in the span of just a few weeks, can outshine every other star in its entire galaxy combined. The galaxy might contain hundreds of billions of stars, each burning steadily for millions or billions of years. And for a brief time, this one explosion outshines all of them at once. The light pours outward in every direction, a sphere of brilliant white and blue energy expanding through the dark at the speed of light. The color of that light tells a story. In the first moments after the explosion, the supernova blazes in ultraviolet light, the kind of high-energy light that human eyes cannot see, but that telescopes can detect easily. As the days pass and the expanding shell of gas cools slightly, the light shifts toward blue and white, then toward yellow. Astronomers watch these color changes carefully. The way the light fades and the precise curve of that fading is one of the most useful signals in all of astronomy. Here is why that matters. Every type Ia supernova fades in almost exactly the same way. The brighter the explosion at its peak, the more slowly the light fades afterward. This relationship is so reliable, so consistent, that astronomers use these explosions as measuring tools. They are called standard candles, meaning objects whose true brightness scientists already know. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Type Ia supernovae let astronomers measure distances across hundreds of millions of light years with remarkable accuracy. This is how scientists discovered one of the most stunning facts about the universe. In the late 1990s, two teams of astronomers were using type Ia supernovae to map the expansion of the universe. They expected to find that the expansion was slowing down over time, pulled back by gravity. Instead, the distant supernovae appeared fainter than they should have. They were farther away than the models predicted. The universe was not slowing down. It was speeding up. Something was pushing everything apart faster and faster. Scientists called this force dark energy, and to this day, no one fully understands what it is. The light from dying white dwarfs revealed it. The explosion itself happens with stunning speed. The white dwarf reaches the Chandrasekhar limit, that critical mass of about 1.4 times the mass of our Sun, and carbon fusion ignites throughout its entire body, almost simultaneously, not in one spot, everywhere at once. The energy released in that fraction of a second is greater than the Sun will produce across its entire 10 billion year life. The white dwarf does not collapse first, the way a massive star does before a different kind of supernova. It simply detonates. The shock wave moves outward through the star faster than the star can respond. In less than a second, it is over. The white dwarf is gone. What remains is not a neutron star, not a black hole. Nothing is left at the center. The explosion is so complete that it scatters the white dwarf's entire mass outward into space. That material, rich in iron and other heavy elements forged in the final nuclear fire, drifts outward for thousands of years. It joins the gas and dust of the surrounding space. Eventually, over vast stretches of time, that material may find its way into a new cloud of gas. That cloud may collapse. A new star may form. Planets may gather around it. The iron in that new solar system came from a white dwarf that once circled another star. In another time, in another part of the galaxy, the light from its death traveled for millions of years before anyone was there to see it. That light carried information. It carried distance. It carried the secret of an accelerating universe. It carried the raw material for future worlds. A single white dwarf, at the very end of everything it had left to give, lit up the dark and told us where we are. Not all white dwarfs go out in a blaze of light. Some speak in a quieter way. They pulse. They breathe. They send out slow, steady waves that ripple through their entire body, from the surface all the way down to the core. These white dwarfs are called pulsating white dwarfs, and scientists have spent decades learning to listen to what they say. The pulsing is not random. It follows a pattern. The star dims slightly, then brightens, then dims again. This cycle can repeat every few minutes. Some pulsating white dwarfs complete a full cycle in as little as 100 seconds. Others take closer to 20 minutes. The rhythm is steady enough that scientists can set a clock by it. What causes this? The outer layers of the white dwarf are not perfectly still. As the star cools, its surface passes through certain temperature ranges where the gas behaves in a special way. At those temperatures, helium and hydrogen in the outer layers absorb energy, then release it, then absorb it again. This creates a kind of squeeze and release, like a slow heartbeat working its way through the whole star. The star expands just a little, then contracts just a little, over and over again. These waves move through the star the same way sound waves move through a bell. When you strike a bell, the vibration travels through the metal and rings outward. The shape of the bell, the thickness of its walls, the material it is made from, all of these things shape the sound it makes. A white dwarf works the same way. The waves that move through it carry information about what is inside. Scientists call this field astrocosmology, the study of starquakes and stellar vibrations. It lets them see inside a star without ever touching it, by watching how a pulsating white dwarf brightens and dims. Scientists can measure things they could never observe directly. They can estimate the thickness of the hydrogen layer sitting on top top of the star. They can probe the temperature of the deep interior. They can even get a clearer picture of how fast the star is rotating, because the spin of the star slightly changes the timing of the pulses. All of this from watching a distant point of light flicker in a telescope. There are several distinct families of pulsating white dwarfs, and each one pulses at a different stage of cooling. The hottest pulsating white dwarfs are called Dwarf stars, named after the first one discovered in the constellation Virgo. These are newly formed white dwarfs, still blazing at temperatures above 100,000 degrees. As they cool, they pass through a second pulsating phase, and then a third. Each phase has its own rhythm, its own character, its own set of things to say. One of the most remarkable things about these pulses is how stable they are. Over years of observation, scientists have tracked the timing of the pulses down to extraordinary precision. And in some cases, they have noticed the timing shift ever so slightly. The pulses arrive a fraction of a second earlier or later than expected. In some cases, this tiny shift reveals the presence of a planet. A planet orbiting a pulsating white dwarf will tug on the star as it moves, pulling it slightly toward us and then slightly away. That motion changes the travel time of the pulses just enough to detect. Scientists have used this method to find candidate planets orbiting white dwarfs, worlds circling the cooling remains of dead stars. The idea that a dead star still has something to say is one of the most quietly astonishing things in all of astronomy. The fusion is gone. The light is fading. The star is slowly becoming something cold and dark, and yet it still vibrates. It still sends out waves. It still carries information across the light years, patient and steady, waiting for someone to listen. In a way, the pulsating white dwarf is like a song that keeps playing after the singer has left the stage. The energy that drives the pulses came from the original star, stored in the structure of the cooling body, slowly working its way out. The star is not truly silent. It is just speaking more softly now, in a language made of light and time, and the gentle rise and fall of its own surface. Scientists are still learning to read that language. Every new pulsating white dwarf they find adds another voice to the conversation, and each one tells a slightly different story about what it is like to be a star at the very end of its long, slow cooling, still reaching outward, still making itself known. Some white dwarfs do more than vibrate. Some of them carry something even stranger, a magnetic field so powerful it would be almost impossible to imagine standing next to one. A magnetic field is an invisible force that pushes and pulls on certain materials. Earth has one. It is what makes a compass needle point north. The sun has one too. But the magnetic fields around some white dwarfs make Earth's field look like a whisper next to a thunderclap. Most white dwarfs have magnetic fields that are fairly modest. But a special group, scientists estimate somewhere between 10 and 20% of all white dwarfs, carry fields that are enormously strong. The strongest ones measured so far reach up to 1 billion Gauss. A Gauss is simply a unit used to measure magnetic strength. Earth's magnetic field sits at around half a Gauss. 1 billion Gauss is not just stronger, it is in a completely different category of existence. Here is where the mathematics becomes beautiful. The strength of a magnetic field follows precise, predictable rules. It does not appear randomly. It scales with the size of the star, the speed of its rotation, and the way its interior is structured. Scientists can write down a set of equations and predict with real accuracy how strong a white dwarf's field should be based on what they know about the star that made it. The universe is not guessing. It is calculating. When a star collapses into a white dwarf, it carries its original magnetic field with it. But the star has shrunk enormously. A field that was spread across a star many times wider than the sun now gets compressed into a body roughly the size of Earth. When you squeeze a magnetic field into a much smaller space, it gets stronger. The math behind this is called magnetic flux conservation. The idea that the total amount of magnetic force is preserved even as the space it occupies shrinks. The field has nowhere to go but inward, so it concentrates, it intensifies, it becomes something extraordinary. Think of it this way. Imagine spreading a thin layer of paint across a large canvas. Now fold that canvas down to the size of a postcard. The paint does not disappear. It stacks up. It becomes thick and vivid where it was once thin and faint. A white dwarf's magnetic field does something very similar. The original field, already vast, gets folded into a tiny space and emerges far more powerful than it ever was before. These magnetic white dwarfs have a name. Scientists call them MWDs, short for magnetic white dwarfs. They are not rare curiosities. They are a real and significant part of the white dwarf population, and they behave differently from their quieter cousins in ways that scientists are still working to fully understand. One of the most striking effects of such a powerful magnetic field is what it does to the star's atmosphere. Normally, atoms in a white dwarf's thin outer layer behave in predictable ways. They absorb certain colors of light. They emit certain colors. Scientists can read those colors like a fingerprint and identify exactly what the atmosphere is made of. But in a magnetic white dwarf, the field is so strong that it actually changes how atoms behave. It shifts the colors they absorb. It splits spectral lines, those precise color signatures, into patterns that look nothing like what you would expect from a normal star. The field rewrites the fingerprint. This is not a flaw in the data. It is the mathematics of electromagnetism doing exactly what it should. When a charged particle, like an electron, moves through a strong magnetic field, the field exerts a force on it. That force changes the particle's path. It changes the energy levels inside the atom. And those changed energy levels produce changed colors of light. The equations that describe this were worked out more than a century ago. Scientists today use those same equations to measure the strength of a white dwarf's field just by looking at the light it sends across the light years. There is something deeply satisfying about that. A star billions of miles away, long dead, still cooling in the dark. And yet, the light it sends carries a precise mathematical signature that tells us exactly how strong its invisible field is. The universe encodes its own measurements into the light it produces. All we have to do is learn to read the numbers. Magnetic white dwarfs also tend to rotate more slowly than non-magnetic ones. Scientists believe the magnetic field acts as a kind of brake, gradually slowing the spin over long stretches of time. Even the rotation follows a rule. Even the slowing down has a rate that can be written as an equation and checked against observation. The universe, it turns out, is very good at keeping records. White dwarfs are very good at keeping records too. And one of the most remarkable things they record is time itself. Scientists use white dwarfs as cosmic clocks. Because a white dwarf cools at a known, steady rate, astronomers can look at how dim and cold a white dwarf has become and work backward. They can calculate how long it has been cooling. That gives them the age of the white dwarf. And from that, they can estimate the age of the star cluster or galaxy where it lives. This is a delicate and precise kind of science. It depends on everything working just right. The cooling rate must be well understood. The starting temperature must be known. The composition of the star must be accounted for. Change any one of those variables, and the clock gives the wrong time. But when all those conditions are met, white dwarfs become some of the most reliable age-measuring tools in all of astronomy. Some of the oldest white dwarfs found in our galaxy suggest that the Milky Way itself is at least 11 billion years old. Others in ancient clusters called globular clusters, tight, spherical groups of very old stars that orbit the outer edges of our galaxy, point to ages of 12 to 13 billion years. These numbers help anchor our understanding of when the universe itself began. The universe is thought to be about 13.8 billion years old. The oldest white dwarfs we have found are not far behind. They formed when the universe was still young, from stars that lived and died in the early cosmos. They have been cooling ever since. They carry the memory of a time before our sun existed, before our solar system formed, before Earth was anything more than a cloud of drifting gas and dust. Think about the precision required for any of this to work. A white dwarf must form in the first place, which means its parent star must have been the right size. Too large, and the star explodes as a supernova and leaves behind a neutron star or a black hole instead. Too small, and the star may not have evolved far enough yet to shed its outer layers. The window for producing a white dwarf is specific. It requires a star of roughly the right mass, living for roughly the right length of time, dying in roughly the right way. Then the white dwarf must cool undisturbed. If it has a companion star nearby, material may fall onto its surface and alter its temperature. If it collides with another object, the record is disrupted. For a white dwarf to serve as a reliable clock, it needs a long, quiet life with nothing interfering. The universe must cooperate. And yet, across billions of years, many white dwarfs have done exactly that. They have cooled slowly and steadily, alone in the dark, keeping perfect time. The fact that we can read that time at all is a product of careful science built over generations. Astronomers in the early 20th century worked out the physics of how electron pressure holds a white dwarf up. Later scientists calculated the cooling curves. Others built instruments sensitive enough to detect the faint light of stars that have been dimming for 10 billion years. Each generation added one more piece to the method. The balance involved is worth sitting with for a moment. The cooling rate of a white dwarf depends on how easily heat can escape from its interior. That depends on its composition, its mass, its surface gravity, and the thin atmosphere sitting above it. All of those factors interact. A slightly different composition changes the rate. A slightly different mass changes the surface gravity, which changes how the atmosphere behaves, which changes how light escapes. The system is sensitive in ways that took decades to fully understand. And yet, the universe built these objects with enough consistency that the method works. White dwarfs across the galaxy cool in ways that follow the same physical laws. The same equations apply to a white dwarf in a distant globular cluster as to one in our own stellar neighborhood. That consistency is what makes them useful. It is also what makes them beautiful. There is something quietly astonishing about this. The oldest objects in the galaxy are also among the most useful for measuring the galaxy's age. They are not loud or dramatic. They do not pulse with energy or blaze with fusion. They simply cool. They simply wait. And in their slow, patient dimming, they carry one of the most important numbers in all of science. How long the universe has been making stars, and how long it has been making the conditions that allow something like us to look up and ask the question. And yet, for all that we understand about white dwarfs, there are places where our knowledge grows thin. There are questions that remain open. There are objects sitting quietly in the dark that we have only just begun to see clearly. And what we find when we look at them is strange and beautiful and not yet fully explained. The coldest known white dwarfs sit at the very edge of what our telescopes can detect. They have been cooling for so long that they barely glow at all. Some of them emit almost no visible light. They shine only faintly in infrared, which is a kind of light our eyes cannot see. A warm glow that sits just below the red end of the color spectrum. To find them, astronomers need specialized instruments that can pick up this dim, slow warmth from across the void. Even then, many of these ancient stars likely remain hidden from us. Scientists believe there are cold white dwarfs out there that we simply have not found yet. The coldest white dwarf ever measured sits at a temperature of around 3,900 degrees Fahrenheit. That sounds hot by everyday standards. But for a star, it is extraordinarily cold. Our own sun burns at roughly 10,000 degrees at its surface. A freshly born white dwarf can reach 200,000 degrees or more. To cool from that blazing, start all the way down to 3,900 degrees. Takes an almost incomprehensible amount of time. The white dwarfs we find at these low temperatures are among the oldest objects in the known universe. They have been cooling for somewhere between 11 and 12 billion years. They were already ancient when our solar system formed. What makes these cold, dim stars even more fascinating is what happens inside them as they cool. At very low temperatures, something remarkable begins to occur. The carbon and oxygen atoms inside the white dwarf start to lock into place. They stop moving freely and begin to arrange themselves into an ordered structure. The interior of the star begins to crystallize. It becomes, in a sense, a solid. Scientists have found evidence of this process happening inside real white dwarfs, and it raises questions that are still being worked through. Exactly how does crystallization change the way a white dwarf cools? Does it slow the process down? Does it release extra heat as the atoms settle into their fixed positions? The evidence suggests yes, but the details are still being studied. There is also a mystery in the numbers. When astronomers survey large groups of white dwarfs and plot their temperatures and brightnesses on a chart, they find something unexpected. There is a cluster, a kind of pileup, where more white dwarfs appear than the models predict. This happens at a specific temperature range, and scientists believe it is connected to crystallization. As the interior freezes, the star releases a small burst of energy, which slows its cooling temporarily. This means white dwarfs spend a little extra time at that temperature before moving on. The pileup is real. The explanation seems solid, but the precise physics of how crystallization unfolds inside these dense, strange objects is still an active area of research. Then there is the question of what we are missing entirely. The coldest white dwarfs are so faint that our current telescopes struggle to find them beyond a relatively small region of space. We can only see them clearly if they are fairly close to us. The ones that are farther away, scattered through the outer reaches of the galaxy, are simply too dim to detect with confidence. This means our picture of the oldest, coldest white dwarfs is incomplete. We are working with a partial sample. Future telescopes, including some already being planned and built, may change this. They may reveal a population of ancient, crystallized stars that we currently cannot see at all. This is one of the things that makes astronomy so quietly thrilling. The universe does not give up all its answers at once. There are layers of the sky that we have not yet seen clearly. There are objects that have been sitting in the dark for billions of years, waiting for us to build the right instrument, to look in the right direction, to ask the right question. The coldest white dwarfs are not failures of our knowledge. They are invitations. They are the universe holding something back, just slightly, as if to say that the story is not finished. There is still more to learn. There is still more to see. And somewhere out in the dark, crystal star the size of Earth is cooling so slowly that it will outlast almost everything else we know, carrying its secrets patiently into the deep future. That crystal star is not finished changing. Even now, as it drifts through the dark and slowly loses heat, something is happening deep inside it. Something slow and quiet and almost impossible to imagine. The carbon at its core is beginning to freeze. Not like water turns to ice on a cold morning. Something far more structured, far more precise. The carbon atoms are locking into a tight, repeating pattern, one by one, over billions of years. Scientists believe that in the most ancient white dwarfs, this process is already well underway. The core is solidifying into a form of crystallized carbon that is, in its structure, very much like diamond. This is not a poetic comparison. It is what the physics actually predicts. When carbon cools slowly enough and sits under enough pressure, its atoms arrange themselves into a crystal lattice, a perfectly ordered grid of particles held in place. On Earth, this is how diamonds form deep underground, under tremendous heat and pressure over millions of years. Inside a white dwarf, the conditions are even more extreme. The pressure is enormous. The cooling takes far longer, and the result, scientists believe, is a crystal core that could span thousands of kilometers across. A diamond the size of a planet, sitting quietly at the center of a dying star. The idea was first proposed decades ago, but it took careful observation to find real evidence. In 2019, astronomers studying a group of white dwarfs noticed something unexpected. A cluster of these stars seemed to be releasing more heat than they should have been for their age. They were cooling more slowly than the models predicted. The best explanation was that something inside them was releasing energy as it solidified. The latent heat, the warmth given off when a liquid becomes a solid, was slowing the cooling process. This was the crystallization happening in real time, or at least in astronomical time, which moves far more slowly than anything we experience in a human life. This discovery changed how scientists think about white dwarf ages. If crystallization releases heat and slows cooling, then some white dwarfs are actually older than they appear. temperatures suggested one age. But their true age, accounting for the extra heat from freezing, was older by billions of years. This means that when astronomers use white dwarf temperatures to estimate the age of a star cluster, they must now account for this pause in cooling. The crystal core is not just a beautiful detail. It is a variable in the math. The freezing does not happen all at once. It starts at the center, where the pressure is highest, and the temperature, though still enormous by any human standard, is low enough for the crystal structure to take hold. Then it spreads outward, slowly, over timescales that dwarf the entire current age of the universe. A white dwarf that is already partly crystallized today may not finish freezing for trillions of years. The outer layers, still liquid or semi-liquid, will keep shifting and settling as the solid core beneath them grows. It is a transformation happening in deep, slow motion, invisible to any instrument we currently have, inferred only through the math and the faint signal of released heat. There is something deeply calming about this image. A star that once burned with the fury of nuclear fire, that swelled into a red giant and shed its outer layers in a glowing cloud, now sits in the dark and slowly turns to crystal. The violence is long over. What remains is this quiet, patient process of becoming something new. The star is not dying in any dramatic sense. It is settling. It is organizing itself at the smallest possible scale, atom by atom, into one of the most ordered structures in nature, and that order will last. A crystallized white dwarf is extraordinarily stable. Nothing inside it is reacting. Nothing is burning. The crystal lattice holds everything in place. Barring a collision or some extraordinary outside force, a fully crystallized white dwarf could persist essentially unchanged for longer than we can meaningfully picture. Long after the stars around it have burned out, long after galaxies have drifted apart, the crystal remains. This is the future that waits for stars like our sun. Not explosion, not collapse into a black hole. Something quieter. A slow cooling, a slow freezing, a gradual transformation into something harder and more permanent than the star ever was while it burned. The fire becomes a crystal. The light becomes structure. And deep future of the universe, there may be more of these crystal remnants drifting through the dark than there are active stars shining anywhere in the sky. And beyond even that crystallized state, there is one more chapter. It has not been written yet, not anywhere in the universe, but physics tells us it is coming, and the waiting itself says something profound about where we are in the story of everything. A crystallized white dwarf is still warm. Not warm the way a fire is warm, not warm the way our sun is warm, but it still holds heat. It still glows faintly in the dark. Given enough time, even that last glow fades. The temperature drops lower and lower, degree by slow degree, across timescales that make the current age of the universe look like a single breath. Eventually, the cooling white dwarf would stop emitting light altogether. It would become something that astronomers call a black dwarf. A cold, dark, solid remnant. A dead star that no longer shines in any wavelength of light. Here is the remarkable thing. No black dwarf exists anywhere in the universe right now. Not one. The universe is not old enough to have made one yet. The time required for a white dwarf to cool completely into a black dwarf is estimated to be somewhere around 250 years or longer. That number is almost impossible to hold in the mind. Our universe is roughly 13.8 billion years old. A quadrillion years is about 70,000 times longer than that. The oldest white dwarfs we can observe, the ones that formed earliest in the history of the universe, are still glowing, still warm, still visible. The universe has not had nearly enough time to finish cooling even one of them all the way down. So every white dwarf we have ever seen, every one we have ever measured, is still in the middle of its long cooling process. The endpoint, the black dwarf, exists only in our equations. It is a prediction, a destination the universe is slowly moving toward, but has not yet reached. There is something deeply calming about that. We live in a universe that is still young enough to be full of light. The white dwarfs are still glowing. The stars are still burning. The story is still being told. When black dwarfs do finally form, far in the future, the universe will look nothing like it does today. Most Most stars will have long since burned out. Galaxies will have spread apart. The sky, if anything were there to see it, would be nearly dark. The black dwarfs would drift through that darkness like stones, cold, silent, extraordinarily dense, each one carrying inside it the crystallized remains of what was once a living, burning star. And inside each of those dark remnants, the atoms would still be there. The carbon, the oxygen, the trace elements that settled into the core over billions of years. The same atoms that were forged in the nuclear fires of the star's long life. The same atoms that, in some cases, were scattered by earlier supernovae and gathered again by gravity into a new star. Those atoms do not disappear. They do not stop being part of the universe. They simply wait, locked in crystal, in the cold and the dark. This is where the perspective opens up completely. The atoms in a white dwarf were not always in a white dwarf. They were in a nebula once. Before that, in a star. Before that, scattered through space. Some of them were forged in the very first stars, enormous and short-lived, that burned out before our galaxy even formed. Those ancient stars seeded the universe with the raw material for everything that came after, for new stars, for planets, for oceans, for living things. The calcium in your bones was made in a star. The iron in your blood was forged in stellar cores and scattered by supernovae. The oxygen you are breathing right now was built in nuclear fires billions of years ago and released into space before our sun even existed. You are not separate from this story. You are made of it. A white dwarf is a star that has finished its active life and settled into something quieter. A black dwarf, when it finally forms, will be a star that has given everything it had to the universe and now rests in the dark. But the atoms it holds were never truly still. They moved through nebulae and stellar cores and planetary surfaces, and perhaps through living things. They will move again in ways we cannot predict, across timescales we cannot fully picture. The universe is patient. It has time. And in that patience, in that slow cycling of matter through every form it can take, there is something that feels very much like grace. Grace space is a quiet word, but it fits. A white dwarf does not go out in a single flash. It does not vanish. It simply gives, slowly and steadily, across spans of time that dwarf anything we can hold in our minds. And what it gives does not disappear. It spreads. It drifts. It becomes part of something new. When a white dwarf cools, it releases heat into the space around it. That heat is real energy, radiated outward in all directions. It warms the thin gas of the surrounding nebula, the glowing cloud of material the star shed long ago. That warmth helps shape how the gas moves and clumps. And when gas clumps, gravity pulls it tighter. And when gravity pulls it tight enough, a new star can begin to form. The white dwarf, even in its long silence, is still part of the process. The planetary nebula that surrounds a white dwarf is one of the most beautiful objects in the known universe. It glows in rings and shells of soft color, pinks and blues and greens, lit from within by the white dwarf's ultraviolet light. These nebulae last only about 10,000 years before they fade and scatter. That sounds like a long time. On cosmic scales, it is the blink of an eye. But in that brief window, they seed the surrounding space with carbon, nitrogen, oxygen, and other elements built inside the star over billions of years. Those elements become the raw material for everything that follows. Scientists have found white dwarf stars near the centers of ancient star clusters, groups of stars that formed together billions of years ago. The white dwarfs in those clusters are among the oldest objects we can directly observe. By studying how cool they have grown, astronomers can calculate the age of the cluster itself, and from that, they can estimate the age of the galaxy. A single cooling star, sitting quietly in the dark, becomes a clock for the entire Milky Way. Our own sun will become a white dwarf one day. In about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a dense, glowing core. That core will be roughly the size of Earth. It will shine for billions of years more, slowly dimming. The planets that remain may orbit it in the cold and dark, or they may be gone. We do not know yet, but the core of our sun, that white dwarf, will carry within it the carbon and oxygen that were forged during its long life. Those atoms will persist long after everything we know has changed beyond recognition. There is something deeply settling about that. The universe does not waste. It transforms. Every star that has ever burned has left something behind, whether it is light still traveling across space, or heavy elements scattered into a nebula, or a quiet white dwarf slowly releasing its warmth into the void. Nothing is lost. It only changes form. Right now, as you rest, the universe is doing exactly what it has always done. Stars are forming in cold clouds of gas. Other stars are swelling and shedding their outer layers. White dwarfs are cooling by fractions of a degree across millions of years. Galaxies are turning slowly and steadily, like enormous wheels in the dark. And somewhere in all of that turning, on a small blue planet orbiting an ordinary star in one quiet arm of the Milky Way, you are breathing. Your chest rises and falls. The oxygen filling your lungs was made in stellar cores long before our solar system existed. It traveled through space, through nebulae, through the early Earth, through oceans and forests and living things. And now it is here, inside you, keeping you alive. You are not a small thing in a large universe. You are a piece of the universe, shaped by the same forces that built the stars. The calcium in your bones, the iron in your blood, the carbon that forms every cell in your body. All of it was forged in stellar fire and carried here across billions of years. A white dwarf is a star at rest, still present, still warm, still part of the story. And you right now are also at rest, still present, still warm, still part of the story. The universe is vast. It is ancient, and it holds everything gently, including you, in the slow and patient turning of all things. Close your eyes. The stars are still out there. They always will be. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.